So I'll hand over the microphone to Tom, and he will introduce our second speaker today.
Thank you, Harry. Aloha, everyone. Really thrilled to have Jeff here. I've known Jeff, I think, for more than 20 years. And part of the reason for that is even though he's been based at these high latitude institutions, or maybe because of that, he does seem to show up at a lot of tropical meeting venues. For example, he was here in Hawaii for at least one meeting at East West Center some years back. And in 2014, we both attended a small meeting, focus meeting on tropical hydrology in Borneo. And that's where I snapped this picture of him in his natural habitat out in the field. You can see there on the slide. So I just had to put that in, and I succeeded because he said it embarrassed him. So anyway, Jeff is now a professor of hydrology and the associate director of the Global Institute of Water Security at the University of Saskatchewan in Canada. And he's told us that that is by far the largest water institute in Canada, and it is quite large. It's pretty amazing. Before that, he was at Oregon State University, where he's a Richardson Chair in Watershed Science and University Distinguished Professor. His work, as most of you probably know, is focused on field-based runoff processes in various venues around the world and in leading measurement techniques and looking for new ways to understand dominant controls on rainfall runoff behavior. He's published over 300 papers and he has recently published a book, which sounds very interesting, entitled Navigating an Academic Career, a Brief Guide for PhD students, postdocs, and early career faculty. I did some checking today and found in Google Scholar, he has over 29,000 citations of his work. His current H index, according to Google Scholar, is 89, which puts him in very elite company. You know, for comparison, I'm quite proud of my 49 H index. So he's way above that. And I did count 78 of his publications that have at least 100 citations, and he has 252 with at least 10 citations. Jeff is an elected fellow of Canada's National Academy of Science, which is called the Royal Society of Canada. He's also a fellow of the AGU, American Geophysical Union, and the Geological Society of America. He's received numerous other national and international awards, which I'm not going to go into because I don't want to take up too much time. I will mention that he has served as a few years back as president of the AGU hydrology section. And he was the president, he has been president of the IAHS, International Commission on Tracers. I would also like to mention that he has told me that he would love to arrange an extended visit, stay here as a visiting scholar at Water Resources Research Center, post-pandemic, of course. And so we'd love to arrange that. Anyway, Jeff, welcome, and thanks very much for joining us in our Water Resource Research Center and Ikiwai seminar series.
Thank you very much, and for that very kind introduction. Harry, thank you so much for the invitation, and Tom, thank you very much again for the kind introduction. What I'd like to do for the next 45 minutes or so is talk about the terrestrial water cycle, the catchment water balance, something that we all learn about in hydrology. And I'm coming to you from Canada, where perhaps our hydrologic cycle is a little different to yours right now, at least. We might need some people to mute on the other end if you're just to avoid the noise, if that's possible. Thanks. Anyway, this is our current scene in the river that runs through town, kind of a view from where my condo is located. But as Tom mentioned, I'm coming to you from the Global Institute for Water Security, and we're co-located with our National Hydrology Research Center. This is the federal water operation that manages our gauging networks and many other activities in water. And the Global Institute was started about 10 years ago, and it's growing now to several hundred full-time and part-time researchers. So it's a pleasure to meet all of you virtually, and we'd welcome reciprocal agreements or meetings in the future. We're going to start off our talk in France, in the headwaters of the Seine River. And I'm going to give you a little bit of background on the water balance, and then explore how geology and biology affect this water balance. And we're starting off in the headwaters because this is where the first measurements of water balance occurred. This is now almost 350 years ago, and this is work by Pierre Perrault in a book called Origin of Springs. And this is my prized possession that sits on my bookshelf. It's really a wonderful read, and it tells a story of measurements that he made in this small headwater section, where I've been collecting some samples over the past couple of years as part of my 2019 sabbatical in Europe. But this headwater section, it was about a 145 square kilometer watershed where he made the first measurements of rainfall and runoff. Prior to that, there were many competing theories about why streams continued to flow when it wasn't raining. He measured rainfall in Dijon, in France, not too far from this site, for 6 years. He made measurements of flow in the stream. He calculated the basin area, and he was able to show that there was more than enough precipitation to keep the stream flowing in between rain events. Here's a picture of the watershed. This is mapping by hand. Of course, this is before the kind of maps that we commonly have in modern times. But you can see the outline of the watershed and the stream network inside. And I might just try to, if I can. No, I can't get my mouse. Oh, I think I can. Pointer options. Okay, so here you can see the stream here going to the exit of the watershed. And of course, what he showed was that rainfall was more than enough to sustain runoff. And this is really the origins of what we still do today, and that is the catchment water balance. Looking at the input minus output equals change in storage. And of course, our outputs are not just stream flow, but evapotranspiration. And in some areas, that can be much larger even than stream flow. But this would be hydrology's most important equation by far. Inputs minus outputs equals change in storage. And this is what I want to explore with you today, because mostly we've come at this input minus output piece by looking at rainfall runoff relations and either measuring or modeling evapotranspiration. Here's some rainfall runoff from a small headwater catchment in Southeast Alaska. This is runoff, the dark line. Here's the rainfall hyetograph scrolling along the top. And these are days of the year. And these so-called hydrometric measurements is how we've made our water balance measurements and closed this water balance on an annual basis. So just like your checking account, we're doing our accounting model, and in this case, doing it on the hydrologic year annually. So water balance is closed annually. However, work with stable isotopes in hydrology, beginning probably in the 60s and 70s in earnest, started to look at inputs of isotope composition of oxygen and hydrogen that make up the water molecule. So it contrasts with this hydrometric view, and this is looking at the input in isotopic composition, and the catchment then is something of a filter for that input, and you get a lagging and damping in the base flow, the water that's flowing in the stream in between events. And rather than this kind of hydrometric view that is clocking the pressure propagation through the landscape, this approach is really getting at the velocity of the water molecule as it makes its way through the system. And as you'll see in today's talk, this is at a very distinct time scale to the pressure propagation, much longer for the individual water molecules to make their way through the catchment. Now, and this also is interrogating now changes in storage with time, because the way in which the isotope is dampened and filtered through the system is very much related to storage and changes in that storage. Now, the way in which this these molecules might move down slope is shown in this lovely diagram that Jim Kirshner produced now about 20 years ago. So if we look at an input in blue and we were to look at how this migrates down slope, it gets smeared as this input that's generated in the upper hill slope makes its way down to the lower foot slope. Similarly, rain parcel that might fall mid-slope gets a little bit smeared by the time it gets down into the riparian zone, and then water falling on the riparian zone is moving quite quickly into the stream channel. And what this results in is often something like an exponential distribution where you have some short flow paths and then long flow paths on the tail of this kind of transit time distribution, if you like. So let's look at an example now from a catchment. And we're going to start off at the H.J. Andrews Long-Term Ecological Research Site. This is a catchment in Western Oregon, just west of the Cascades. You can see some prominent volcanoes here you might recognize. And this is a wonderful site because it's now about 70 years of continuous gauging from several catchments of different scale. And let's just look at one scale, and that's the outlet of this full watershed. We'll dive into the middle of it in a few minutes. But what we do with these data is that we measure the input, and this would be input in precipitation that's covering several years. Values are typically lighter in the winter, closer to zero in the summer. So this is representing, in this cartoon, about 6 or 7 years of input. And this damping, what we can do is take one of these transit time distributions. Remember, this is coming from the example I gave you in the previous slide, but we can pick any number of these distributions. It could be the exponential, like we just talked about. It could be a gamma. It could be two parallel linear reservoirs. These are distributions to characterize that storage distribution in the catchment. So let's just say it's an exponential, like I'm going to show in this example. We convolve that input signal with the distribution that gives us the best fit for these data that we sample in the stream. Because of course we can dip our sample bottle in the stream and then send that to be analyzed for its isotopic composition, just like we can with the rainfall. And here's what these data might look like. This is oxygen 18 on the y-axis. The unit is per mil. We won't get too hung up in that tonight. Just think of it as a concentration. This is time on the x-axis, covering a period of about 2 years, and the green dots are the samples we've collected from the outlet of the H.J. Andrews watershed. That faint gray line is that convolution, our best fit line, and the mean of that distribution, meaning if I take now the mean of that distribution here, is 2.2 years. So already we can see that if we're closing our water balance on the time step of a year, which is traditional in hydrology, we already have some issues because our stream flow is over 2 years old in this case. So let's look at how geology affects stream flow and these characteristic timescales represented in the isotope data that we collect. So let's go back to the H.J. Andrews. And now what we're going to do is look at many of these smaller watersheds that are internal to the larger catchment. And we're going to ask, does the water get older as you go bigger? Does it stay the same? What's the nature of that scaling of water ages in the landscape? So here now are these time series. This is 018 on the y-axis, same x-axis as you saw before, covering this period of about 2 years. And these are the different watersheds of different size. You don't need to remember their names, but you can look at some of the different mean transit times. They're varying from a low of about 0.8 years, so just under 1 year, to a high of about 3.3 years. So our question is, does the water get older as the catchment scale gets larger? And that's what these data are showing. Here's mean residence time, or mean transit time, I'll call it, on the y-axis for these catchments. Here's basin area on the x-axis. And what you can see is that there is no relationship between age and catchment area. It doesn't get bigger necessarily as you go up to larger landscape scales like we might have thought of initially. However, If we take these same mean transit times from these watersheds, remember they're varying from just under 1 year to just over 3 years, and we look at the slope length and gradient of those individual watersheds, now that's explaining a very large percentage of the variance of this transit time. So this is saying that it's not related to basin area. Somehow the age scaling for these systems is related to how steep or how long the slopes are. So slopes that are short and steep have very short residence time. Slopes that are longer and flatter have longer residence time. Now let's slide in Oregon from the H.J. Andrews here, if you can see my cursor, to the larger circle. And this is another set of similar catchments. It's called the ALC watershed. It looks and feels very similar to the site I just showed you. It's steep, it's wet, the soils are very, very permeable. If I dropped you in blindfolded by helicopter, you'd be hard pressed to know which system you're in. The forest is similar, about 50-year-old Douglas fir. The one difference though is that geology has changed from these volcanic rocks like breccias over here to meta sediments, mudstones, siltstones, and the like. And if we test that hypothesis that we gain from the H.J. Andrews, no relationship with basin area, everything really related to the steepness and the length of the hill slopes, we're going to test that. But first, I just want to show you that the hydrology is effectively the same. If we look now at 4 years worth of flow data, this is from the H.J. Andrews, so precipitation up here, and these are the hydrographs. Remember, Oregon has a kind of a wet Mediterranean climate, so it rains like crazy through the winter, and then this lovely dry period each summer. Here's the Coast Range watershed. This has been picked for 1 year in 2008, and it's showing very, very, well, 2006, 7, 8, and 9. It's showing you quite similar behavior. It looks similar if you just kind of squint at it a little bit. If we zoom in and really examine it, now I put it in a semi-log scale, so discharge, it's tough to see the difference. In fact, even the rain amounts or precipitation amounts are strikingly similar, even though they're about 120 kilometers away. So we're going to focus on these 2 years. You can see that we're within, 100 millimeters of precipitation in terms of the differences between these sites. So very, very similar rainfall runoff relationships. But when we look at the isotopes and the calculation using this convolution integral technique that I mentioned, we see the opposite behavior. We see no relationship with these topographic measures, and now the area is explaining most of the variance, about 80 to 84% of that variance. So each of the dots represents a different sub-watershed scale. Rather than varying from 1 to 3 years old, this is varying from about 3 to 11 years old. So it's much older, this water, and really no relationship to topography. So here we're learning something that we could never learn from just the rainfall runoff information alone. And of course, it comes down to storage and how sponge-like our systems are. Here in the Western Cascades, at the H.J. Andrews, in this volcanic rock, we're getting things forced laterally because of really poorly permeable bedrock. Whereas on the Coast Range, we're getting things moving deeper, engaging with regional groundwater, and things are getting older as you accumulate more and more basin area. As you can see in the photo with these alternating sandstones and mudstones and more permeable geology. Now let's look at a couple of other places. Last year I spent 2019, thankfully before COVID happened, in Luxembourg at the Luxembourg Institute for Science and Technology. And I was drawn to Luxembourg for many reasons, but one is the geology is so interesting because it's at the edge of the Paris Basin, and this Paris Basin geological system exposes such a wide range of rock types in very close proximity. And the group that I was working with, led by Laurent Pfister, shown here, have taken advantage of that. This is a series of about 16 catchments that they've gauged, and the colors represent different rock types. So there's sandstone, there's mudstone, marl, schist, and many other rock types, and they have clean and mixed expression of these rock types. And if you look at mean transit time on the y-axis against a kind of a bedrock permeability measure, it's very clear the influence of bedrock permeability on the age of the stream flow. So the more permeable the bedrock, the older the water, the sandstones, for instance, and the less permeable the bedrock, the younger the water. And the size of these dots represents the mean annual flow in these systems. So again, we're getting an idea that really geology is destiny, to quote Gordon Grant, in these kinds of systems when you start thinking about things that affect the storage component of the water balance. But one interesting thing that we found here, and this was, of course, the other reason I was so attracted to Luxembourg, the beer is so good. This is their local brew, Bofferding. They have a well in one of these catchments. It's down over 200 meters, but they draw groundwater from the sandstone aquifer, and it's been age dated with carbon isotopes to be 33,000 years old. But if we go back and just remind you of the mean transit times on the y-axis in the streams, these are on the order of what, half a year to maybe a couple of years old. What's going on? We got 33,000-year-old groundwater, and we've got very young water in the stream, relatively speaking. Scott Giuseco spent some time in my lab here in Saskatoon. He's now an assistant professor at UC Santa Barbara. He's looked at this in detail, meaning the age of deeper groundwater, and he's done a meta-analysis for several sites in North America and Europe. And he published a lovely paper on this a couple of years ago. And if looking on the y-axis, this is depth below the water table. So now he's been able to scan data across 6,500 groundwater wells that have this carbon age dating information. And he's going down quite deep with this data set. But the take-home message is that not only does it get older as you go deeper, which is maybe what one might have expected, but by the time you get down to about 250 meters, 2/3 of the water pumped from these wells is fossil water, water that's pre-Holocene, older than 10,000 years. And when you think of our watersheds, our steep headwaters, you know, 250 meters is not that much relief in these kinds of mountainous systems. And this really was I think, a sobering message for me. We'll come back to this a little later. So what this is suggesting to me is some compartmentalization of this water cycle. And certainly when we look at the role of geology, I think it's influencing the connections and maybe lack of connections and maybe the windows of connection between different pieces of the system. And this is a theme I'll continue to refer to as we go along. The other piece of the story, though, I wanted to talk about is how now biology affects the stream flow and compartmentalization. So we've looked at the lower boundary with geology. Now we're looking at the upper boundary, because as we said, and we know from our water balance, evapotranspiration can account for quite a considerable amount of the outflow. In many cases, like here in Saskatchewan, we're a semi-arid system, and evapotranspiration is much, much greater than actual flow in the stream when you look at the sum total of the output. Now, just like a stream in a catchment, we can sample the transpiration stream in a tree by sampling the xylem water. And of course, the tree is drawing water from the roots, and it's driven by Ohm's law in terms of these potential gradients. And water is moving through the tree. And what we're going to look at now is, where's the tree getting its water? How old is that water? Where is it coming from in the system? And this upper boundary and how it might influence stream flow. And just like the rainfall runoff hydrograph, you know, we have a hydrograph, if you like, of sap flux. And this is driven by, you know, gradients in vapor pressure and stomatal processes in the plant. Of course, it's a biological process. This is what we're going to look at now with our stable isotope tracers. We're going to use stable isotopes to go after the water in the transpiration stream of the tree. We're going to use O18 and deuterium again, or 2H. These are the two isotopes that we're typically using in isotope hydrology. Again, oxygen and hydrogen, of course, are part of the water molecule. But we can look at them together rather than just the time series that I showed you earlier, and we can see more into the water cycle, meaning precipitation usually falls on a line. We call it the MWL, or meteoric water line, and departures from that line are telltale signs of evaporation, fractionation, things that happen when water in a glass or in a lake or in the soil profile even undergoes evaporation. The remaining water plots on a shallower slope below that meteoric water line. Or if you're in Hawaii and you're on, I don't know, the island of Lanai, and you're raking in a lot of fog water that's maybe condensing on trees and dripping down into the soil, you know, that water might plot above the line. And I know that Martha Scholl and Tom and others at your institute have been looking at that and using stable isotopes to target that occult precipitation. Here we're showing it, but now looking at the other side, and that's the evaporation side. And this was a paper published by John Gibson, just showing what this looks like for big rivers. You know, for the Amazon basin, you start in the headwaters, and these are samples taken longitudinally downstream to where it meets the ocean. It's falling on this meteoric water line, and then it's starting to drift off due to evaporation of that surface water. The Murray-Darling River Basin, water in that stream looks quite evaporated from the get-go. And looking at the Rio Grande, the headwaters are falling on the line, but then the water in the channel is exposed to all this evaporation, and what remains, just like the water glass, is plotting off the line. Now we're dealing with small watersheds, and all of our waters usually plot on the meteoric water line. This is an example from a site in Mexico, another tropical site. Tom is right. It's probably because I'm in Saskatchewan that I'm drawn to tropical sites. But what you can see is that the rain is falling along that line. And just like we saw in the sine wave, now it's expressing itself by stretching out along that line. The soil water we might sample with a suction lysimeter is kind of a lagged and damp version, and the stream water is even further damped, just like you've seen so far in some of the time series I've shown. Okay, so this is a bit of background on how we're going to now look at plant water isotope composition. We're going to go back to the H.J. Andrews again. We're going to zoom in on one of these small catchments. This is a 10-hectare watershed. Watershed 10 is its name. It's a pretty straightforward naming convention. This watershed has 50-year-old Douglas fir, and my colleague Renee Brooks from the EPA started sampling these trees. And one day at coffee, we thought, well, we should compare our numbers. You know, I had very much like this site in Mexico and other sites I've been working on, all of my samples from this watershed looked like this falling on that meteoric water line. We were curious to see where her plant water samples, meaning the xylem water from these Douglas fir, plotted. And what she brought to coffee that day looked like this. Well, just the green triangle she brought to the first coffee meeting. And we looked at that together and thought, what the heck's going on? All of the water I'd ever sampled, whether it was soil water or groundwater or water from a trench, had all fallen on the meteoric water line. She had these green triangles that were often out in outer space. From my perspective, what water could they possibly be using? So we mounted a survey to sample soil water again, but this time not using my suction lysimeters that as hydrologists, we often use to sample the vadose zone. Here we took physical samples going from shallow out here on the right and progressively deeper down to where it touches the meteoric water line. And we extracted that water with this technique called cryogenic extraction. It's the same technique that she used to get the water out of the xylem tissue. And it gets all the water out down to about minus 15 megapascals. So really gets all the water out. And of course, what's happening is the trees are using that water, that more tightly bound, if you can call it that, certainly not the mobile water that we get with the suction lysimeters. So the trees are using rather different character of water that we would see in the stream. And we might say the trees are not using the water we see in the stream, and the water we see in the stream, the trees don't seem to be using. This was a real shocker, at least for me, as a hydrologist who really came of age in this whole notion of translatory flow and the movement of water through the system, similar to the diagram I showed you from the 2D hill slope earlier, and calls into question a lot of the mixing assumptions we make in catchment hydrology. And what these data are suggesting is that we have this water along the meteoric water line, the rain in blue, and the stream is a lagged and damp version. And similarly, the soil water is stretching out on an evaporation line where things are fairly evaporated, very shallow, but of course, no evidence of evaporation as you go deeper away from the atmospheric evaporation front. And the plants are a kind of a lagged and damp version of that input, and a really different behavior to what we were expecting going into this study. Our model really was one of head scratching and desperation to explain these findings. Again, it's a wet place. You see the photo from the site here in the upper right, although it's seasonally wet and then seasonally quite dry. So what we hypothesized was that during the fall wet up, meaning recharging the soil water after a very long dry summer, we recharged that tightly bound water that the trees have tapped into and used for photosynthesis through the summertime. Then the rainy season turns on and water is just coursing through these soils, but seemingly not mixing with that stored water that was recharged in the first couple of events of the fall rains turning on. And now 6 months later, when the trees really get active again in terms of transpiration, what do they use? They use that water that was recharged many months earlier. So this is something we call eco-hydrological separation. And we tested this hypothesis with a meta-analysis, and this was led by Hawai Evaristo, who's now an assistant professor at Utrecht University in the Netherlands. And what Hawai was able to do was to identify about 50 data sets that we could access that had the isotope data, not just for groundwater and stream flow and precipitation, but also plant water and soil water. So we really posed this eco-hydrological separation as a hypothesis to reject. We didn't believe it would be operational across a variety of sites. We thought somehow it was more of an artifact of this kind of interesting Oregon wet Mediterranean climate. And what we found was it was much more widespread than we would have imagined. So here's groundwater and stream flow falling on that meteoric water line, and now the plants are drifting off that line and following the soil water data that's also drifting off that line. So this idea of eco-hydrological separation and a notion of compartmentalization or lack of connectivity. It was interesting. In 2015, Steve Good, who's now an assistant professor at Oregon State, published a paper in Science, and it was coming at this from a remote sensing perspective. This is the Aura satellite, where they make deuterium vapor measurements from space, and they then resolve those measurements with measurements of ground-based or ship-based deuterium composition in vapor to try to close their deuterium mass balance. Anyway, it's a long-winded way of saying that they too found this lack of connectivity. And this lack or limited connectivity, this is quoting their paper, between soil and surface water fundamentally structures the physical and biogeochemical interactions of water transitioning through catchments. So really having to invoke something like this eco-hydrological separation to be able to resolve and close their balances. So what this is suggesting, I think, is that not just the compartmentalizations happening in the subsurface, but also in the surface, with the upper boundary condition in terms of transpiration and water uptake. Now, I've really not given you any mechanisms, and there are many groups working on this. And what I'd like to give you just a taste of is some current work we're doing. And this is with a group at EPFL in Lausanne, Switzerland. They have a lovely lysimeter here that has a pair of willow trees in it. And what's really nice, this is collaboration with Paolo Benetton and Andrea Ronaldo. We can add tracer to these lysimeters, as you see in the animation on the right-hand side, and we can measure everything. We can measure the matrix potential in the plant, in the subsurface, so we can use Ohm's law to see where the plants or what's driving maybe decisions on uptake. We can label the water with our deuterated water, and we can make careful measurements of storage change, water content, and so on. And I just want to show you some very brief data from this, and also using dendrometer bands along with sap flux sensors to understand tree water deficit and how that might be influencing behavior in terms of water uptake by the plant. And this is work led by a current PhD student of mine, Magali Nahemi, and Magali has a paper coming out showing how if we look on the y-axis, this is plant water deficit on the y-axis. So we're using these dendrometer bands and we're correcting for tree growth over this period from May to June to July, this kind of period of growth where we're measuring everything coming in and out of the lysimeter. We start off with a period of no water deficit, and then we go into a dry spell where we have kind of an intermediate water deficit, and then a period of significant water deficit. And these are the isotope kind of portions that the plant is using. It's using a blend of mobile water, like water we'd see in the suction lysimeters, but then the low mobility water from these extractions in the shallow and deep soil. But what you can see is it's changing depending on the level of moisture or water deficit in the plant. In other words, how thirsty the plant is really influences what water it goes after. So look over here on the right, there are different decisions being made by the plant in terms of water uptake. So looking at these three periods, we think that plant tree water deficit is one key factor in terms of what's driving the type of water that the plant is using. What about transit time? We've not really talked about kind of things we discussed at the catchment scale in terms of the time it takes to move through the plant. If you're a plant physiologist, you can put in sap flux sensors and you can calculate something like transport velocity. This is from a stand just north of Saskatoon in the boreal forest we have here. This is work of Magali and colleagues. Here's sap flow on the y-axis for a one-day period. And this is suggesting that the transit time of water from the roots to the shoots, if you like, in this boreal stand is about 16 days. That's the transit time through the plant itself. So that's the transit time through the tree. And this has been backed up with tracer additions as well. The question is, what about the transit time through the soil as well, bringing that into play? Because we don't just inject water into the fine roots or mycorrhizal fungi, they're extracting it from the soil, which is itself a blend of water from many rain events past. This is some work that Hawai has recently published from Biosphere 2, where we can do controlled experiments. Here we're working in the rainforest biome. Tom, there's my daughter Megan, who you met in Borneo. And here we're doing an experiment where we did a 10-week drought and then added in a rainfall label where we could look at that combination, not just of the plant water transit time, but the transit time of water from the first rain striking the forest floor to when it's taken up by trees. So this is concentration on the y-axis on this plot you're seeing, and this is covering a period of several months from October 2014 to April 2015. it's a complicated plot, but what I want to show you is if we look at the kind of the spiked water addition you see here, what you see is a real blend of time it takes for that tracer to be observed in the trunk of the tree, in that xylem sampling that we did. And in some cases, not just days or weeks, but even, you know, a month or two to be able to see the breakthrough of that tracer. And this is a combination of hydrological processes through the soil, and then also the very different wood densities and transit times through the plant itself. This is ongoing work, and again, other groups are doing this as well, and controlled experiments are very helpful to get at some of the combinations and permutations of these controls. The last example, although I want to leave you with before I move to wrap up, is going a little bit more detail at the age of the water. And here we're actually going to a place where we can really try to create some natural experimental conditions. And this is on the Loess Plateau of China. And as you may know, this is an area of deep wind-blown material, this silty loess material. It's not, you know, meters of unsaturated zone. It's many, many tens of meters. In fact, the water table is probably 100 meters below the surface here. And these deep, deep unsaturated zones are an ideal lab because if we look at the left-hand plot, this is 0 to 20 meters. You can actually core into the loess 20 meters. The students I've been working with regularly set world records for hand augering into soil. Just imagine going down 20 meters. And here we're seeing a profile now of an isotope. This is not deuterium or oxygen, this is tritium. So 3H, it's a radioactive tracer. And this is a very helpful tracer because the plants, they're mostly apple trees that are planted here for an afforestation effort. These plants are rooting through this bulge that you can see of tritium. And that bulge of tritium relates to the thermonuclear bomb peak here that we see in precipitation around the world that peaked in 1963. And then we had the Comprehensive Test Ban Treaty and world tritium levels in precipitation started to fall. So the x-axis is going from 1940s to, you know, about 2000 or so. This place here is 1963. So basically this tritium profile is essentially the input turned on its side. So it's taken from 1963 to now for that plume, if you like, to make its way 8 meters into the soil. Now these trees root down to about 13, 14 meters in a desperate search for water. So if we look at the stand age, these trees, by the time they're getting to about 25 years old, and this is the depth now, 0 to 25 meters, you can see they're really mining that deep vadose zone for water, and eventually they run out of gas and die. But here at 25 meters, or 25 years old, these trees are putting roots down, you know, up to 20, 25 meters. Now we've age dated this because we picked here 5 trees and we've run a Bayesian mixing model, basically relating what we see in the apple that we're making apple cider with. So rather than sampling the sap flux or the xylem water, we're sampling the water in the apple. And what we find is that that water is about 29 years old, very old. But again, its ascent is through the tree, but it's also down through the soil profile. And for me, this is really the heart of these complex eco-hydrological questions, mixing or fusing the hydrology and the ecology. All right, let me try to move to wrap up. Maybe first a quote from Perot. It is to experiments that we owe the finest knowledge we have concerning the things of nature. I think this was true, you know, almost 350 years ago, and it's still as true today. And I think, you know, based on what I've been describing today, our job is to really understand this kind of compartmentalization. It's all connected, of course, but it's understanding how, when, and where things connect and disconnect, I think that could maybe be a different way of coming at the water balance. It's not so rhythmic as we see in our grade 10 geography studies when we first learn about the water cycle. And the isotopes are showing by measuring the velocity of the molecule, something really quite different to our more traditional hydrometric approaches. Now, it's an exciting time in this field because, you know, I showed you some really kind of old school, if you like, approaches to quantifying transit times. Man, in the last decade, there's just been such an exciting proliferation of models, particle tracking models, other types of storage selection functions that I think are proving very helpful, not only for the hydrological community, but also the ecological community when looking at these combined ages in the system. So this is very exciting. And I think what we're moving towards, and maybe is our ultimate goal, is an age-based water balance. So not throwing the water balance baby out with the bathwater, but maybe coming up with a parallel age-based water balance. This is a lovely review that Matthias Springer has recently published, kind of looking at what this might look like if you look at the age on the y-axis, and then these pieces of the critical zone, and how all of this gives us characteristic ages, almost like the demographics of the critical zone as we begin to think about our systems. And this is, I think, really going to pave the way for new eco-hydrological understanding. Now, if you are a geologist, you probably know that there is some much older water out there. For instance, in Canada and South Africa, deep drilling has shown billion with a B year-old water. This is work by my colleague Barbara Sherwood-Lawler at University of Toronto. You know, very, very old water exists in our system. And I think what this is suggesting, along with the kind of data I was, you know, representing tonight, is, you know, we also need to get to grips with where's the bottom of our watershed. This was a small commentary that Laura Condon led a couple of months ago in Water Resources Research. And it's trying to bring together now surface water hydrologists, groundwater hydrologists, to really think about, yeah, where is that bottom? Are some of those very old waters, like the pre-Holocene waters that Scott Giuseco has been finding, remember below 250 meters, 2/3 of that water is fossil water. How connected is that fossil water to our watersheds at different scales? These are all really rich questions, I think, for future studies. So I'll end with this slide and say that I think really we need to move beyond the catchment water balance and come up with an age-based version. And perhaps the way forward is to ask these questions of how geology and biology control the water we see in our streams. How can chemistry help answer these questions? You know, I've just shown a couple of very small examples from my isotope world, but of course there's a whole periodic table out there that could maybe shed further light on the nature of these transit times, mixing, connections, disconnections, and getting at how and when these compartments are connected. So with that, Tom, I'll leave it there and say thanks for listening. Thank you.
Harry, you want me to handle this?
Oh,
Maybe
okay,
I'll stop.
sure. Yeah, thank you so much for the great talk. And there are several questions. Okay, let me read one.
While Harry's looking, I just want to say thanks very much, Jeff, for an outstanding presentation and really opening our eyes to this whole issue of, I think sometimes called the two water worlds, and, you know, the mobile and immobile water, and the mystery of why the trees seem to prefer the difficult to get water, at least under some conditions, and all the implications of that really is an exciting new area of study in hydrology. So thanks very much for presenting.
My pleasure. Harry or Tom, do you want to read the questions, or do you want me to pick some, or how should we do that?
I think Harry's gonna.
Yeah, I can do that. So
Okay,
first
great.
question was the general audience. It's about the general concept of catchment. So what is the catchment? Is it like a watershed? In your first slide is about starting with the catchment and then just moving to the watershed.
Yeah. Well, I guess the catchment is a natural unit of the landscape. It's a place where we can make a measurement in the stream, and we know that if we trace a line to the highest topography that contributes to that stream flow, then any water falling into that zone ultimately will make its way to the stream, and outside of that zone will go to another stream or river. Of course, this is presupposing that there's not inter-catchment groundwater flow, and that can be a big assumption in some geological systems, but it's really the spatial way that we close our water balances. And of course, the whole world is broken up into catchments of different sizes. You know, you have the Mississippi River, which is enormous, but within the Mississippi are a multitude of different sized streams and catchments. And in fact, I think Rich Alexander at USGS showed in a paper a few years ago about half the flow and half the nitrate export at the larger river basins are coming from those headwaters, those small catchments, the water towers, if you like, of the larger river basins. That's why the catchment is often the focus.
Thank you. The second question is about a little more the water development purposes. So water development purposes is very difficult to obtain an accurate estimate of groundwater recharge. In light of that, could Dr. McDonnell suggest a method to establish a reasonable low-angle estimate of the groundwater recharge on which government and private developer could base their plans?
Yeah.
Yeah.
No, it's a very good question. You know, some countries have actually gone to using groundwater age as a sustainability and developmental metric. New Zealand, for instance, has adopted this. This is based on work by Uwe Morgenstern and the Geological and Nuclear Sciences Institute in Wellington. And they use tritium quite regularly to age date groundwater, and it allows them to kind of sidestep the groundwater recharge measurements that, as you've suggested or said, I think quite correctly, they're enormously difficult to make. But by sampling the age of the groundwater, you can say something of its sustainability. So for instance, you know, if you were to find groundwater that was 10,000 years old, you wouldn't necessarily be able to do that with tritium, but that might tell you by definition, that's maybe not a sustainable groundwater source because its age perhaps is a relic of a previous climate or previous recharge environment. Now, there's many, many caveats to that statement, but you might also find maybe some groundwater that you're thinking about for municipal development that's, I don't know, 10 years old, and that might be something to give you confidence that the recharge is such that this is a sustainable system, maybe along with some, borehole measurements of conductivity, so you get a sense of what the well might be capable of producing. So anyway, New Zealand has adopted this. Check out some of the work by Uwe Morgenstern.
Okay, thank you. And the third question is during your presentation about the interaction between the basement flow and aquifer and the catchment. So how long does it take for rainfall to reach the aquifer, probably in your case, in your size?
Yeah, well, it's a complex answer to that because it's a distribution of times or flow path lengths. You know, water droplet falls on the ridge of a watershed, let's say it continues percolating vertically, you know, that water molecule could take hundreds or thousands of years to make its way to perhaps the water table or maybe the stream. Whereas water that's falling near the channel or near the top of the water table in a lower foot slope position, you know, that would be a very different kind of characteristic recharge time or transit time to the stream. So it's difficult to answer that, but I think it's one way of coming at that is this transit time distribution. And yeah, I think age dating groundwater has been helpful for a number of activities. For instance, you apply nitrate-based fertilizers and you're wondering, you know, when they might show up in the stream. Lovely work by Dave Genero in North Carolina showing that's really linked to groundwater age that's forming the base flow in the stream. and how long that conveyor belt is before you see that surface applied nitrate showing up in the channel. And it could be years or decades.
Okay, thank you. So the next question is about some Hawaii, the question relevant to Hawaii. So I actually refer this one to the local hydrologist. And the one from Conceptory is that during your explanation about the evaporation. So does the propagation of water through a tree cause a fractionation?
Yeah, well, I'd say some years ago, we might have said no, that transpiration is a non-fractionating process. And, you know, there were some really important papers published in the early 90s. There was a Nature paper by Todd Dawson, who's now at Berkeley, and Jim Ellringer from University of Utah. And they showed just lovely examples of how you could sample the xylem water and relate it to its end member or source contributions in the soil or groundwater. But in recent years, probably starting off in 2006 or 7 and more recently, I think we're realizing that certain trees are fractionating along that transpiration pathway. There are certain interactions between the phloem and the xylem water that under certain conditions you can have diffusion of perhaps fractionated phloem water into the xylem. And yes, there can be issues in terms of the otherwise simple sampling of the xylem water and relating it to its source water in the soil profile. And this is a very active area of research. So there's not really a one-size-fits-all answer. Many species show no evidence of fractionation with transpiration. Some show it intermittently, depending on certain conditions, and some trees are chronically showing evidence of that.
Okay, thank you for the answer. Okay, the next question is about the Luxembourg question. So you mentioned that the third of water from the wells, so the age is about 30,000 years old. So is the aquifer head there on a steady decline? It's like an aquifer exploitation issues also in Luxembourg.
Yeah. You know, I don't know about that particular well in Luxembourg. The pump rate is pretty low. They're very, very conservative in terms of groundwater allocation. So there's no evidence that it's declining. But I guess, again, I made some sweeping statements referring to the Giuseco paper. You know, there's a blend of ages. And in fact, one interesting finding in that paper that Scott had was that of those wells that were showing fossil water, half of them had detectable modern water, meaning some tritium in it from post-bomb tritium. And the question then was, how do you have coexistence of modern water less than 50 years old and fossil water more than 10,000 years old? And there were two hypotheses floated. One could be fracture flow. So you're getting some, you know, more recent water getting down to depth, or the other could just be poor well construction, where maybe you're getting, you know, kind of contamination, as it were, of water flow down the outer annulus of the well during a rainfall event or what have you. So yeah, it's a good question. But in that example, there's no evidence of decline, but that's mostly due to low pump rates.
Okay.
Yeah.
This is the following question about the fractionation effect. So this kind of fractionation effect can be seen in evaporation. So can you actually measure the fractionation effect in the evaporation?
Yeah. I mean, there's good theory for this. There's something called the Craig and Gordon model, and this is the model where you bring meteorological measurements, and you can actually predict, if you know the humidity of the room, you know the starting composition of the water in the lake or the glass. You can predict what that fractionation will be by the known relations between the water in the liquid stage and the water in the vapor stage. So this is it's both measurable and modelable, and the techniques we're using now to make these isotope measurements have also really exploded in recent years. And these so-called laser spectrometers allow us to make measurements not only of liquid, but vapor as well. And this is really a growth area in forest eco-hydrology. Field deploying these instruments into sites to get at local cycling and even recycling of moisture.
Thank you. So the fifth, okay, inundating questions from Ekadi. Is there a chance to improve on current watershed models, which employ a number of semi-empirical equations representing the subsurface using a number of soil and aquifer parameters? And in Hawaii, I have very deep water table with hundreds of meters of unsaturated soil and saprolite with unknown characteristics. Case of contamination in these zones are difficult to access creating a nightmare of the management uncertainty. So, broad comment on the improvement of the watershed model.
Yeah, well, there's many things in that question, but maybe I just say first that these tracers can be additional criteria to evaluate a model, and as you saw, it's a different window into the behavior. So it's non-redundant additional criteria against which to evaluate your model. And this is happening not just in hydrology. There's a regional climate model called NOAA, and NOAA MP now has an isotope-enabled version. This is happening with catchment models, and it's attractive because, it forces you to get to grips with the nature of this question. The fact that we in Hawaii have a very deep water table with hundreds of meters of unsaturated soil and saprolite with unknown characteristics. Yeah, so I guess, you could use isotope tracing to say whether or not you're getting the answers for the right reasons in terms of maybe the time scale of movement through that deep unsaturated zone. Maybe doesn't tell you the physics of it, but it gives you a target or a benchmark against which to compare your estimates. So in that way, I think they have been very helpful for models.
Okay, thank you so much. About the isotope or useful chemicals from Paul. So chemicals explain fatal rainfall, and would it be helpful to bring up the result of the? I really don't know about the geochemistry and
yeah.
So and did you are you aware of this paper, Kennedy and Malcolm?
I'm not aware of that paper, but I think Polly is referring to Vance Kennedy, a USGS hydrologist, and they did a lot of very nice work with stable isotopes in the Matoli River, I think in California. The work I'm aware of was some of the first work that Vance did. He's quite senior now, he's in his late 90s, but Carol Kendall, my friend who worked with him for many years, tells me that Vance is still active and very much engaged with his local watershed council. Anyway, the work that I'm familiar with in the Matoli River Basin is some of the pioneering work Kennedy did with colleagues showing the role of soil water in streamflow generation during rainfall events. And yeah, I would agree that there's probably other chemical end members to get at this, weathering products, more conservative geochemical tracers, reactive tracers. And as I mentioned in my talk, I'm just talking about a few conservative tracers, but there's a whole suite of non-conservative tracers that can be also very helpful.
Okay, thank you. Our last question is from Ura about regarding the Magali's work. So what metric potential define mobile and immobile and threshold for shallow and deep with regarding to shifting proportion of water used during the dry down?
Yeah, this is a big question, and it gets at something I avoided in this talk, and that has to do with extraction techniques. Our extraction techniques are pretty rudimentary. You go in with a ceramic cup and you vacuum it down to 60 inches of mercury and you get water out, but you only get it out of the soil if the soil's has a high water content. Otherwise, that's not enough tension to draw water out of a unsaturated zone under some considerable tension. Otherwise, the cryogenic extraction gets all the water out, but we don't really know the link between the signature of the water chemically or isotopically and its tension. And what we really need is an ability to sample discretely at different points along the moisture release curve. And then I think we can really get at Aurora's question in terms of, gosh, what water are we sampling? Because right now we use these terms mobile or low mobility, but we really don't know how mobile or how low mobility they are. There's also a number of other issues with extraction in terms of how hard you try to extract. That also can affect the signature you ultimately get back. And there are, just so many papers each month coming out on this topic by different groups. So we're learning a lot, but we still have a long way to go on addressing Aurora's good question there.
Jeff, can I follow up just a little bit? How confident are you that these differences you're seeing are not artifacts of the methods that are, they're somehow producing, selectively extracting for reasons you don't, you're not going after? Yeah.
Yeah. No, it's a good question. Well, we're trying to get at that in different ways. I'm working with John Herbon and his group at University of the Sunshine Coast in the Atherton tablelands, where maybe like in Hawaii, on a small plot, you can have hundreds of different species co-occurring in these rainforests. And there, we have very simple and predictable soil water signatures, but very, very different plant water uptake signatures because of this kind of niche segregation, if you like, with all these co-occurring species on the same plot. So we're trying to play games by comparing and contrasting what we see with different plants, almost thinking of the plant as a sampler on its own, to try to maybe get at these issues of how the way we extract or sample affects our interpretation. We're also doing intercomparisons of all the different extraction techniques. So we have not just cryogenic extraction, but centrifugation. There's a vapor bag extraction technique. Neil Bunskard's just developed a new microwave extraction technique. There's hydraulic squeezing. And so we're really trying to, not in all of our studies, but in some, extract in all these different ways and see how that does impact our interpretation. Other groups are going into the field and actually measuring xylem water directly or using vapor techniques to get at things in situ. The one final caveat I'd make in all of this is that for these laser spectrometers, these phenolic compounds, methanol, ethanol, can really screw up the spectra in the laser spec. And this has been really a vexing issue because we're finding that is another issue that can alter your interpretation if you don't detect it. And we've been developing new O17 excess detection techniques to see if we have contamination in our laser specs due to these phenolic compounds. And that would really throw you off if you didn't know it was a problem. It's kind of it's now a known unknown, but maybe before it was an unknown unknown. And to your question, yeah, quite troubling. So it's such a fast-moving area, Tom. It's an exciting time to be alive and studying eco-hydrology.
Okay. Thank you so much for the great talk and also all the detailed answers to the questions. I really appreciate and then giving your talk here in WRRC and EcoWise seminar. Okay, so
real pleasure. Thank you.
Yeah, just add my thanks again, Jeff, and we'll look forward to getting you here in person as soon as we can do so. And you get to sample some of our local beer. I don't think we have any 10,000-year-old water going into our beer, but it's pretty good. So I look forward to that day.
Great. Okay. Thanks very much. Nice meeting you all. Good seeing you.
Thank you so much. Yeah.
Thank you. Aloha.